We are looking at
So yeah, guys, the basic core concept வந்து கம்ப்யூட்டர் வந்துட்டு முடிச்சிட்டோம். So I think now it's time to learn Golang. ஸோ இப்போ கோலங் லேர்ன் பண்ணலாம். ஸோ கோலங் லேர்ன் பண்ணதுக்கு நான் வந்து இந்த சீனியர்ஸ்லின்னு சொல்லி ஒரு சேனல் இருக்கும். இந்த சேனல்லேருந்து தான் நான் லேர்ன் பண்ண போகிறேன். ஸோ ஸ்டார்ட் பண்ணலாம்.
custom functions. The main is also a function, but there will be a thousand. thousands and millions of other functions in a typical life cycle of a program. Now we are looking at one of those functions, how to define functions in Go. Now this is the structure a function follows. First, we have the keyword func. That's how a function starts. Then we have the name of the function, whatever name. Typically, we give a function, the name of the function. Then we have a braces inside of which we'll have parameters, and the parameters will follow the structure, the name of the parameter and the type, comma, the name and the type. Okay, that's the structure we'll follow for parameters. Then we will explicitly have to define the return type of the function. Function. It is mandatory to define what type the function will return. Now we'll explore data type soon, so nothing to worry. Just focus on the function part here. We'll define the return type here. Then we'll start a curly braces in the same line. Then we'll write all the statements here, and we'll end the curly braces. This is how the typical structure of a function looks like. And now we can call the function inside println, and we can provide two arguments of type integer, because we have defined this is an integer type, because Go is a statically typed language, which means all the types are verified and they're checked during. It says cannot use h, and since the defined data types that a function accepts, we cannot use random any data types. See, it has to be an integer. Okay, now if we run this, we get the result 49. 42 plus 7, 49. And that's pretty much all you need to know about functions, how to define functions. So this is the structure you have to remember. It will have a func keyword, then type statement x comma y for the earlier type, because if both the parameters are of the same type, then you can get rid of the type of the first parameter and add it to the end of second parameter. Okay, that's the all about the structure of the function. Go has a feature that a function can return multiple values from inside it. And to demonstrate that, here we have a function called swap. It takes two parameters, and it's in the merged form where both the parameters are of type string. So we have removed the string type from after x, add braces here. Okay, if it's a single value, we can write just string without the braces. If it's more than one value, we have to write braces here. It returns to hello and second is world in this sequence. And sure, multiple values inside A or values to define your function. Go has the capability to return multiple values from a function. Okay. Now there is another way to define your return values in a function. So we have a function split here, which takes one parameter of type integer, and the parameter name is sum, and it returns two values of type integer. But instead of writing it like this, int comma int, we have written it like this. We have, what we have done is we have named those return values with x and y. And with this structure, what happens is when we name our return values, those two variables are initialized. They are initialized with their zero values. Since it is an integer type, now with the start of the function, before anything is executed, before the first line, two variables are implicitly declared. Now we have x equal to 0, y equal to 0. Now let's focus. You have to write return, and what the program will do is it will return Go support. It is very difficult to track. So let's say it's a very large, and now you want to understand what this function returns. Now you go to the first windows, we understand the flow of the program. Right? It just makes things more complicated than they have to be. So for that reason, I prefer to use the explicit return type. So in this case, what should ideally happen is we should just do int, and we should initialize these variables like this. We'll get to the initialization variable part right after this. Now I should do x comma y. Now if we run this program, you're again getting 7, 10. Now if you read this, this is much more readable. You understand about variables. Okay. Now this is how we declare variables in Go. Outside of the function, we can write the keyword var and the name of the variables. And if all of them are of the same type, we can just add the type at the end. If they're not of the same type, we have to add the type after each variable's name. Since all of these are of the same type, we can just write bool at the end. And all these variables are initialized to their zero values. Because in Go, a variable is never in an uninitialized state. It is never in an undefined state or null state. A variable is or whatever the data type is, always initialized to its zero state. So since it is a of type bool, it will be initialized to its zero state, and the zero state of boolean is false. Okay, this is how we declare variables out. outside of a function body, inside a package. This is not inside any function, because that's why this is the only way to declare variables outside of a function. Now, if you're inside a function, we have a couple of ways to declare a variable. The first type is this. The same way we define the variables outside the function using var. Var, the name of the variable and the type of the variable. And this will initialize I to the 0 value of integer. What is the 0 value of integer? It is 0. Yeah. And if we try to print these variables, let's just run it. We get 0, false, false, false. The 0 for I, and since C, Python, Java are all initialized to the 0 value of Boolean, they are all false. Now there is another way to declare and initialize variables in the same statement that is only doable inside a function. We cannot do it outside the function. So we can write it here, I with colon equals to 0. And if we follow this pattern, it is pretty short to write. And this is one of the patterns that you'll use mostly. You'll also use the var pattern. But if you already know the initialization value of a variable, then you'll use this pattern, the colon equals to. And since we know the i's value has to be 7, now we can do this. And if we print down, contains 7 false, false, false. Now this format, this colon equals to format, is only accessible inside the function. We cannot do it outside the function. If you try to do it here, let's do it. So to write it using the var pattern, you can see to it. If you hover over it, it will say expected declaration found here. So all the declarations outside a function has to follow the var pattern. It cannot follow the colon equals to pattern. Okay. Now there is another way to write it using the var pattern. You can say var I equals to 10, and if you print it, it prints 10. And using the initializer, it interprets that I is of type integer. Okay. And this is just a long way of writing the colon equals format, because this is the same thing as writing if you take out var and we just put colon here. So this colon equals to is kind of a syntactic sugar, a short way of writing this var. Okay. If you don't want to go to interpret the type, we can write var I and write string. Now the moment we write the type here, the initializer value has to support this type. Now it says cannot use 10 untyped integer constant as string value. Now we have to make this in a typical Go program. Now, if you have questions now that which pattern to follow when, this is how you should think about it. These are the rules. First rule is if the initial value does not matter and you're fine with it initializing with a 0 value, then go with this pattern, this var I integer. Since it does not matter what the initial value of I is, and we will set the value of I in the course of the program in a later phase, we can initialize it like this. It implies that to the reader of the program, whoever is looking at the program, they now can understand your intention that variable I has a value of 0 when it is initialized, and the initial value of I does not matter, and the value of I is set somewhere later in the execution of the program. So that's the first type. And the second type is if you know the initial value of the variable and it is important, then you can go with this colon equals to. Now, since you know the initial value of the variable I is 0 and it has to be 0 and it is important for it to be 0, then go with this pattern. Okay. The third thing, if you're outside a function like this, then you don't really have a choice. You have to follow this pattern, var c bool. You can also initialize it here, var c true. Okay, those are typically the 3 patterns when it comes to variables that we have available in the language. Now, to get a little concrete idea about how people use variables in a real system, let's go back to our example of FIDER. A couple of examples that we can see using the var form of variable declaration is here. As you can see, these variable declarations are outside of a function. They are in the level of package. They're the package level variables. And that is the reason they have declared it using var, even though they knew the initial value. And in the same way, these variables are declared in the package level, and that's why they are declared using var. And you can find a lot of examples like that. All the variables that are declared at the package level they have to be declared using var. And another example, which is declared inside a function and still uses this pattern of var instead of the short declaration of colon equals to, because they have initialized the variable at this stage, but at this stage the initializing value does not matter. The value that will be assigned to this variable, which is of type error, it is of type error, but the initial value does not matter. We don't have an initial error value. The value will be assigned during the execution of the program. So if you focus here, the value is actually assigned to the ERR variable is at this point. At this point, this function returns an error type in the second return value, and that's what gets assigned to this variable. Okay. So in this pattern, when we have a variable that for which the initial value does not matter, in that case, we can go with this pattern. In the same way, if we look for the colon equals to pattern, let's look for the colon equals to, do a global search, and you can find this pattern pretty much everywhere, because most of the time most of the times we know the initial value of our variables or of our data types. So in that case, we pretty much go with this pattern. For for loops, we have not explored for loops yet, but there also we use this colon equals to, the short declaration form of variable declaration. You can find this example everywhere. This is the go-to method of initializing variables when we know the initial value. Okay, so those are the two things that you have to keep in mind. Eventually, when we do more practice, when we use variables a lot in Go, you'll get it. You'll get which pattern that we use where. For now, just know that these two kinds of patterns exist in a typical Go project. Moving on to the next example, which is of data types. So in this example, various data types are declared. We have Boolean, we have unsigned integer, we have complex, and we are printing the variables and the type here using printf. Okay, and we are using the percentage %t verb. Percentage %t verb is used to print the type of a variable, and percentage %v verb is used to print the value of a variable. There are other words, which is percentage %s to print the value of a string. There is percentage %q to print the value of a string in double quotes or single quotes. Okay, and there are different words that you don't really have to remember. The more you use, the more you will get the idea, and you'll remember to print the type of a variable. And percentage %v verb is used to print the value of a variable. There are other words, which is percentage %s to print the value of a string. There is percentage %q to print the value of a string in double quotes or single quotes. Okay, and there are different words that you don't really have to remember. The more you use, the more you will get the idea, and you'll remember the pattern the next time you need them. So let's see what are the data types that we have on a high level. All in all, let's say Go has 4 major types of data types. The first one is basic. In basic, we have number, we have string, and we have boolean. These are the 3 major categories inside the category basic data type. The second data type that we have is aggregate data types, and these are of types array and struct. Array is basically a collection of similar data types, collection of homogeneous data types. You cannot store a string and a number inside the same array. The type has to be same for all the values inside an array. And inside a struct, in the opposite way, struct is a collection of heterogeneous data types or different kinds of data types. You can store an integer, you can store a string, you can store a boolean, all inside the same struct. So that's the difference between array and struct, and they are called aggregate data types because they consist of different basic data types inside them. Okay? We have the third type, which are called reference data types. Reference types inside them, we have pointers, which we'll explore soon. We have slices, we have functions, we have channels, and we have maps. These are the 5 reference data types, and they are called reference data types because they themselves don't contain the data as a container. They refer to some data type which works in the background, and they refer to that data for functioning. That's why they are called reference data types. They don't have the data in them. They refer another data type to access the data. And we have the fourth one, interface types. We'll explore interfaces later, but they are another major type in Go. So these are the 4 major categories of data types in Go. And inside basic, we have number, string, and boolean. So if you go here in the tour of Go, here we can see we have have slices, we have functions, we have channels, and we have maps. These are the 5 reference data types, and they are called reference data types because they themselves don't contain the data as a container. They refer to some data type which works in the background, and they refer to access the data. And we have the fourth one, interface types. We'll explore interfaces later, but they are another major type in Go. So these are the 4 major categories of data types in Go. And inside basic, we have number, string, and boolean. So if you go here in the tour of Go, here we can see we have boolean, we have string, and we have inside number, we have all. all these categories. We have integer 8 and all these numbers 8, 16, 32, 64 and uint, which stands for unsigned integer, and 8, 16, 32, 64, etc. So what is the difference? What do these numbers mean? These numbers basically help you to decide the size of your variable, How? Let's imagine int 8, we take integer int 8. What this means is this variable can have numbers between minus 127 to 128. And how did I derive this range from this number 8? So this 8 means basically this variable can use 8 bits to represent the number. So 8 bits means 2 to the power 8, which is roughly 256. And 256, since it is a signed integer, we can have negative numbers inside this. We divide this range can be minus 127 to plus 128. That is the range. We can store numbers inside this range in int 8. And in the same way, you can derive what can be the range for int 16 or int 32, etc. And for uint, the unsigned integer 8, what that means is, since it is unsigned, we can only have positive values. So 2 to the power 8, which means 256. So our range can consist of 0 to 255. We can assign numbers inside this range. That's what these numbers mean. What can be the range of your integers? How much size that you want the language to assign for these variables. Now we have other two types, which are integer and uint, unsigned integer. What these mean, for example, if your operating system is of 32-bit architecture, then int will have int 32 in size. And if your architecture is 64-bit architecture, then int will have int 64. Same for uint 32 and uint 64. So the Go official documentation recommend that you should always go with integer and unsigned integer, depending on you whether you need positive values or negative values. You should always go with the system-defined variable units, variable units. But there are times when using int 8 makes more sense than using int, which if you have a 64-bit architecture, which will have 60 in 64. In cases when you exactly know what is going to be the range of your integer value. For example, if you take a look at FIDER and we try to find uint 8, and if you take a look at here, we don't need to understand what's exactly happening in this system, but all in all, on a very high level, we can understand this, that there is a type which has the data type uint 8, and we are declaring some variables of different levels. And on a very high level, without understanding anything, we can say that they need this level type to be the range from debug 1, 2, 3, 4. So maximum 1 to 5. This range is enough for this use case to define different levels of logs inside a backend system. Okay. So in this case, if they had gone with the system-defined unit, which is int or uint, then that would have assigned the uint 64 unit. And that range is a little bit too much for this use case. So 2 to the power 64 can have these many numbers, which they don't need for this use case. So for this, they went with the smallest available unit for unsigned integers, which means unsigned integer 0 to
2 bit, please.
255. So since they know their range is going to be available to in 30, what that means inside, we divide this reference 27 to this. Variable can use 8 bits to represent the number. So 8 bits means 2 to the power 8, which is roughly 256. And 256, since it is a signed integer, we can have negative numbers inside this. We divide this range can be minus 127 to plus 128. That is the range. We can store numbers inside this range in int 8. And in the same way, you can derive what can be the range for int 16 or int 32, etc. And for uint, the unsigned integer 8, what that means is, since it is unsigned, we can only have positive values. So 2 to the power 8, which means 256. These mean, for example, if your operating system is going to be the all in all, we can say that so system. Okay. So in this case, if they had gone with the need for this use case, so for this, they went with the smallest available unit or unsigned integer. In the worst case, 10 or 12, if they come up with more levels in their logging. So worst to worst case, 50, going to go ridiculous levels. It cannot exceed more than that. So for this use case, going with a uint 8 saves a lot of memory for your system. So it's pretty much common sense that if you beforehand know the range of your integer, if you know what is the maximum value you can assign to your integer, go with that range. Go with that range. So that's the mental model you can use to either go with any of the numbers, any of the weighted units. Now, while working on backend systems, when dealing with user data or data that you are not very sure of what is going to be the size of those integers, then you can safely use integer. It is not a very huge performance effect, since Go official documents also recommend you to use the system-defined unit. Okay, that's the mental model you should have. Then we have byte, which is an alias for uint 8. Bytes are also used to represent strings inside Go. We'll explore more on that later. Then we have rune, which is an alias for int 32, and it is used to represent UTF-8 characters inside a Go program. Floating point values. Value 8. This is a program which defines a boolean, unsigned integer 64, a complex data type. Then we are getting the type and the value. And if you run this, then we can see the type values false. And for any strings, the zero values an empty string, a empty quote. Okay? Those are all the 3 basic data types, and those are all the 0 values that you have to remember. There is another 0 value, and we are printing here using %v. %v prints the value with quotes. Okay, and if we run this program, we can see so 0, 0, false, and empty string. So in this case, if we change this from %q to %v, then what happens? We don't see the quotes anymore. So if we want to print the quotes, then we have to use %q. That's the use of %q word. So in case of strings, it will explicitly print the quotations. Okay. Next up, we have type conversion. Type conversion basically applies in statically typed languages like Go, because unlike dynamic languages like JavaScript or Python, conversions are not done implicitly by the language. You cannot assign a float value to an integer value, and you cannot depend on the language to implicitly convert it. You have to explicitly convert the value. That's all there is to it. To understand that in Go, every data type needs to be explicitly converted into another data type. There is no implicit conversion, even though a number satisfies. So in this case, let's say you have an int 64 value and you have an int 32 value. Even though both are the same numbers, let's say both have the value 32, and this variable is k, this variable is v. Even though you have this use case, you cannot assign the value of k to the value of v, because the internal data type is int 64. Even though the values are same, they're both the integers and they both satisfy each other, you still have to explicitly convert like this int 64, the name of the type, and pass the value of k. Then you can assign it to v. This is the format that you always have to follow. It does not. not matter whether the type internally satisfies us or not. You have to explicitly convert the types before assigning. Okay, so in this example, what's happening is we are type conversion, and usually you don't have to worry about this while you're developing applications. You will get these errors while you're developing in your IDE itself. You won't get it during, so you don't have to actually worry about it. You will get hints from a compiler to fix your errors. So you can go back to it, and we are using a short declaration form using colon equals. In this form, we don't define the type of the variable explicitly. We let the language go. In this case, if we hover over it, you can see that the type of value is integer because we have assigned 42. So if we change this to 42.7, and if you see this, now this is a float 64 value. And in the same way, if you change this to a string type of the variable with the initializer statement, in the later phase, if you type to do b equals to 9, in this case, you will get the error that cannot use 9 untyped in constant, integer constant as is. String value. So a value, you always have to initialize a constant, otherwise it's an error. So constant have some properties. First thing is they are of course constants, and what that means is you cannot change the value of a constant in a later phase of a program. The second thing is they are they are evaluated during compile time, and that's the reason we always have to assign some initializer value to a constant, because the values of constants are evaluated during compile time. They are not evaluated during runtime or when the program is executing. During the compilation phase only, the program will know the value of the constants. So if you try to run this, we get all these values printed. And what if we try to change this? Truth equals to false. And if you hover over it, we'll get the cannot assign. What is the difference? When do we use variables and when do we use constants? What is the mental model there? So basically, every time that you have some hard-coded value, you have some predefined value, whether it is a string or a number or a boolean, because constants can only have these three data types in them. A constant can be a boolean, a constant can be a string, or a constant can be a number. These are the only three data types constants are allowed to have. So when you're developing, if you have a use case where you have a hard-coded value, you have a port that you want to listen to, or you have a URL that you want to make a request to, or you have an allowed set of values that you want to validate against, any kind of hard-coded value. So instead of using the hard-coded value as it is, you can name the value using a constant. And that implies that this value does not change ever during the course of your program execution. And it has a semantic meaning, and it also has a runtime meaning, because constant cannot change. So if we look at the use of constants in our example, of a real-world example, you can do a search here, const space. And if you try to go files, so as you can see, it's kind of implementing an enum pattern using Go, using constants. So it has an allowed set of values. We will see what are enums and how to implement enum pattern in Go later on when we are building projects. But as of now, you can see that these are some hard-coded values, and in order to name them in a meaningful way, we are using constants. In the same way, we are using 1, 2, 3, three hard-coded numbers to a meaningful name, that role visitor, role collaborator, role administrator. Okay. In the same way, there are hard-coded values here. There are hard-coded values here. So there is the pattern. You have a hard-coded value. You want to name them. You want to name them in a meaningful way. Those are the scenarios when we use constants. Next up, we have loops. Now, unlike other programming languages, Go only has one loop. This is for loop. We don't have while loop. We don't have a do while loop. We don't have any other those loops, because the for loop is semantics. By changing the syntax of the for loop a little, we can implement all those patterns. Now, how does a loop work? By the way, a loop just means executing a set of instructions again and again until a specified limit in order to reduce the boilerplate code. Instead of writing these statements again and again until like 10 times, we can use the construct of loops, which is available in every programming language, to run the same statement 10 times. Okay. So how does this loop work in Go? We are here declaring a variable of sum, a variable named sum, which is of type integer. If you hover over it, it will say integer because the initializing statement is 0. Now we are initializing a variable named sum. Now this is how the loop works. The first statement is the initializer statement. It is some kind of expression. So here we are initializing a variable called I, and I is only usable inside these curly braces. It is only usable inside this scope. This is called lexical scope, and I only works inside this. And after every iteration, i's value changes. A new instance of I is created. Okay, the previous instance is destroyed. Now this is the first expression that is that runs with every iteration. Second, the iteration, the whatever statement inside the loop construct, this is executed. After the execution, this statement runs. We change the value of I. We increment the value of I. Then at the end, we check this condition, whether this condition is true or false. If this condition is false, the flow of the program using this tool called debugger to better understand how the program works, to investigate the flow of the program, basically. Now, if you run this, VS Code has a inbuilt debugger for Go. Now we can run this. And in first iteration, we have I with value 0, and we have sum with value 0. We have a breakpoint here. The program stopped here at the first iteration. Now using this, we can go to the second iteration. So after I click this, we came outside this loop, and here we are checking whether i's value is smaller than 10 or not. Since i's value is 1 after the first iteration, the condition is true. That's why the loop runs again. And if we click on this, now i's value is 1 at this point, because in the previous iteration, i's value was incremented to values from 0 to 1 after the end of the statement. Now, since you're entering this loop again, now i's value is 1. After this, i's value and will reach the loop. And then we'll end up with a while go. So if you run this, we have value will print. And so that's how and will end. So the next iteration. And this will break and we'll reach the end statement. So we'll break out of this loop and we'll reach the end of the main function. And after this, the value will print. And so that's how a for loop, a typical for loop works in Go. Now, if you want to implement the while loop from other programming languages, we can just get rid of the first two expressions, the initialization and the increment, the expression, and then we'll end up with a while loop, which basically has a pause statement and a condition and execution statements. So this is how you do while loop in Go. So if you run this, we have 1024 is the sum. So until this condition is true, this loop will keep running. And once this condition is false, it will break out of this loop and we'll see the print statement. And at this point, what if we take out the condition? If we take out the condition and what if we run this? At this point, our program is stuck in an infinite loop. An infinite loop basically means because there was no condition to break out of this loop, our program never exits and it is stuck inside the same set of calculations. So unless you have a specific condition at this step, the program will never exit. The program will never exit out of this loop unless there is an explicit break statement here. But if add a condition, if sum is greater than 100, then we break. We add a condition here for breaking out of this loop if the value of sum goes out of 100. And now if you run this, you can see that once the program reached 128, in the next iteration, the condition was true and it broke out of this loop. Now this pattern, if you're wondering why do we need infinite loops in the first place, since it hangs the program, we have some patterns, especially when we get to the concurrency chapters. There we have some patterns where we are constantly listening for signals from different Go routines and all. There we use this pattern of infinite loops. So we keep listening for signals and all. And the moment we get some signal, we break out of this loop. That's how this pattern works. So you should know that we have a way of implementing infinite loop, which is not always bad. There are uses for infinite loop also. Now it is a very good point to show if conditions. It is pretty simple to wrap your head around. We have a condition which starts with if, and whatever the condition that is provided after that, there is no basis. You have provided a condition which should evaluate to either true or false. And if it is true, then this statement will run. Otherwise, it won't. That's pretty much all there is to if condition. In the same way, in the for loop, in the first part, we could assign, we could initialize a variable, we could call an expression in the first part, in the first semicolon, here, for here, I, this part. In the same way, in the if statement also, in the first part, we can initialize or we can call an expression in the first part. This variable v will be valid in the if condition, will be valid in the if lexical block. So for example, if we try to access v here, we try to see, let's say k equals to v. Now if we hover over it, it says undefined v, because it is only valid inside this lexical block. It is not valid outside. So it is a very nice way of initializing and checking errors that we use with this feature of if. It reduces some amount of boilerplate code because of this pattern. We can initialize a variable and we can check a condition. And if that condition is true, then we get inside the if block. If not, then this is not executed. So this is a very nice way to reduce boilerplate code. The same way, after if, we can also use else. If this expression is evaluated and if this condition is true, then we get inside if block. If this condition is false, then we get to the else block and this part is executed. And as I said, the value of v is only available inside the if block and inside the else block. We cannot use the value of v outside the if and else. this block. And now I think it's a good time to take a look at some examples in the real world of how we use for and how we use if conditions and if else conditions. And here we can see they are looping over the number of CPUs and doing something. Does not matter what they're doing. And this is how people use for loops. And here you can see they're dynamically taking the length of this variable and initializing this loop and running these executions. Okay, this is how for loops work. And let's look at if. And this is how typical if, else if, and else conditions work. This is basic programming stuff. If this condition is true, then this part is run, or if this condition is true, then this part is run. Otherwise, if there is an else condition, that is run, or the program just keeps executing. Typical if-else behaviors that we have in other programming languages. Nothing too special here, or nothing to remember here. Go also has a switch case. In the first part, you can evaluate some expression, and this variable is available throughout the scope of this switch block. It is not available outside it. Now, using this, you initialize this variable using runtime.go operating system, this environment variable that is available to your Go programs by default. And you use this variable as a condition. You are checking, check the value of OS, this variable, and you're checking different values. Whether the value of this variable is this string, Darwin, or if the value of this variable is Linux, or if none of these cases satisfy, then it reaches the default block, and this block gets executed. Otherwise, if one of these statements are true, if one of these cases are true, then that part gets executed and this breaks. It does not proceed further. It breaks out of this switch statement. And if we try to run this, we are getting Go runs in OS X because this matches our Go operating system. This environment matches Darwin. And that's why we are getting this. And the moment it matched this case, we came inside this block and this statement got executed and it broke out of this switch statement. Okay? This is the typical behavior of switch statements. Now, this is another example of a switch case. A switch case condition can also be an expression. It can be a constant string, it can be a number, or it can also be an expression. If this will get evaluated, and depending on that, we'll get inside any of these blocks. And the moment any of the case statements are true, we get inside that block and the statements are executed and we break out of that loop. And if we try to run this, since today is Saturday, we'll probably get today. When is Saturday? It means today because we came inside this block. statement got executed and it broke out of this switch statement. Okay? This is the typical behavior of switch statements. Now this is another example of a switch case we'll probably get today. When is Saturday? It means today because we came inside this block. There is another pattern with switch, which is a replacement for writing these kind of code. Let's say if you have if condition and we are checking something, then we have the block, then you have else if. When you are checking something, then you have another block, then you have another else if. You're checking something, we have another block, then at the end we have else. So instead of writing like this, we have this construct in a switch statement. So we can initialize a switch. So this condition is checked from true, then the default one is executed. So if we try to run this, we get good afternoon because it's not 5 yet when I'm recording this. But now we have a very interesting concept which is called differ. And this is very unique to the language Go, and other programming languages might have different implementation of the same concept, but in Go we call this differ. Why do we use this concept, the differ concept? Is before that, let's just execute this function and we get first this is printed, the hello part, and then this is printed. What exactly is happening here is the moment you use the keyword differ and then you provide some expression. It can be a function call, it can be an expression, whatever is provided in this part, this gets stacked in, let's say, some kind of stack. So we have a stack here and this is pushed here. So this world, this instruction of print world, this stack is pushed here, and then this expression is pushed into the stack and the program starts to execute normally. Whatever instructions that come after it, they are run sequentially, however you can expect your program to run. So that's why after this evaluation, it did not print yet. This does not get executed yet. It is just evaluated and pushed into a stack. Now we reach at this stage and this is printed here. You can see the first hello. Now after this, the main program is finished. There are no more statements to run. At this point, the main function returns. We call this the main function returns. At this point, what the Go programming language does is it takes the stack and it starts to call all these functions, call all these expressions that were provided throughout the function execution, all the defer statements. They can have multiple defer statements in a function, and all the defer statements are pushed into the stack one by one, and the Go program starts to call them in that order by popping them off the stack. So that's why after the function return, after all the statements were executed, we see this getting executed, the print ln to world. So the first world hello is printed and then the world is printed. Now to understand this concept of differs and the stack of differ a little better, we have a loop. And in this loop, what we are doing, we are calling differ multiple times. Let's say 10 times. We are calling the differ statements 10 times in this for loop. And let's just execute it and then we'll understand what happened here. So say go and you can see first the counting that got printed, then we have done, then we have 9, 8, 7, 6, 5 okay, in the reverse order. Now let's understand what exactly happened here. Okay, minimize this. First thing, the first statement in the function counting. First we saw this got printed in the console. Okay, this is done. Then we reach here in the for loop. With each iteration, let's say now we have a stack here. We have a stack where the Go programming language pushes all the differ statements, the call of all the differ statements. So in the first iteration, the i's value is 0 and we call differ. So this function, this expression is pushed into the stack. So we have print 0 here. Okay, this instruction is pushed into the stack. Second iteration, zeros, the i's value is 1. Now print 1 is pushed here. Then 2, then 3, then 4, then 5, then 6, 7, 8, 9. 7, 8, 9. Okay. And at this point, this statement, the for loop statement, the condition is false and it breaks out of the loop. And we reach here. At this point, counting, after printing counting, we see done getting printed here. Okay. And then there are no more statements in the program to execute. At this point, the main function returns. And when returning, the Go programming language runs all the deferred statements of that function. It runs all the deferred statements of that function when returning from the function. So at this point, what it does is it pops out of the stack. Since it's a stack, we push all the values on top of each other. It pops in that order. So that's why after seeing counting, then done, we see 9 getting printed, then 8, 7, 6, 5, 4, 3, 2, 1, 0. In the reverse order, all of them getting printed because the Go programming language pops all the elements from the stack in the order they were pushed. Now you should have a good idea of how differ works. Differ is basically pushing the execution of some function calls, some expression into a temporary stack. And when the function returns, the Go programming language executes all the functions. Now the question is why? Why do we need differs? Like what are the use cases? Why would we need to execute statements before returning up the function? Why not execute them explicitly? Why not? Why not just execute them here? Now there are two answers to that. One is sometimes it is easy to forget running some statements in when we are developing, when we are writing code. For example, when we are opening a file. So in SCOJA systems programming language, we have constructs to open files and read data from different sources. Now, after you open a file, you have to explicitly close the file. Otherwise, there will be memory leaks and your program will eat a lot of memory because there will be a lot of open files in case you are reading a lot of files in a for loop. In that case, every time you open a file, you have to explicitly close it. So what happens? You open the file, let's say I write in pseudocode, you open the file, and at the end of executing all your complex calculations, you have to remember to call close on that file, on that function. Now, there are two things that can happen here. Either as a human error, you can forget to close the file. That is a very expected scenario. A lot of times there are a lot of human errors in a program and we can forget, and we do forget. And it can be a file also, or it can be a database connection that we need to explicitly close while we are returning from the program. Otherwise memory leak happens. There are a lot of instances where after you start something, you have to explicitly stop it. The start and stop comes sequentially. The stop is mandatory. In these scenarios, you have to remember calling the close functionality. So either you can forget it, or during the execution of the program is broken. The program throws error. It panics. To talk in Go's terminology, it panics. We have not explored what is a panic yet. But panic basically means Go's way of throwing an exception. Go does not have the concept of exception, where the flow of the program completely changes. But you can think of it as an exception. It throws an error and the program stops executing. That is basically a panic. Exactly what the name sounds like. So let's say you opened the file or you opened the database connection. You were running some instructions here. You were running some business logic. And at some point, before you called close, at some point your program panicked. It threw some error. It panicked. And instead of going in this flow and calling close at the end, it panicked and it stopped the flow of the execution and it directly took this path. Now you never got to call close because in your mind, the way you had imagined it was, you'll open the file and you'll run some instructions and in the end you'll close it. Now you remembered to close it, but since your program panicked, since your program threw some error and returned from that statement, you never got to close the file. And all these database connections and all these open files are still there in the memory. Now you have a memory leak problem in your app. So for these use cases, the Go programming language has given the feature of defer. Now you don't have to remember to close the files, to close the database connection at the end of your function. Okay, what you can do is you can open the connection, open let's say file, and in the next line what you can do, you can say defer close file. Now it won't instantly close the file because as you saw, the function is not called instantly when you call it using defer. It is evaluated and it is pushed into a stack. So the moment an error occurs, at some point here, the Go programming language is configured in a way that the moment an error occurs, it starts executing all the functions that were in the defer stack, it starts popping all these functions and it starts executing them. That is a construct provided by the Go language itself. So for that functionality, for that feature of, in case of a panic, you still want to execute these statements. You still want to close a file in case of an error. In case of a panic, you still want to close your database connections in case of a panic. For this use case, we can use defer. And it's also readable. You are opening a file and you're instantly deferring the closing of file. So it does not matter what happens after a few hundred lines of code. The closing of file will always happen because of the way Go is built. The defer functions are always executed when the function returns. It does not matter it is successful or it panics. We can take a look at some examples of how people use defer in the real world. So if you search for defer here, you can see some functions where, as you can see, people are setting some database, and in the next line only, they are calling defer. So that after, so this is a test in Go for your information. Don't have to worry about what all these are, but this is a test. Initially, they are starting some database connection, and in the next line only, they are deferring the teardown, basically the closing of the database connection. So that during the flow of this test, it does not matter if it errors out or not. This closing of database connection is always executed, and is also readable that you started the database connection here, and you close the connection in the next line. So after all these executions, the Go program runs this part, the teardown of the database. Okay, and you'll find a lot of differs in this project, which have different meanings in different contexts. But you should have a good idea by now what defer means. Basically, pushing the execution of a function to the last statement, and ensuring that it always runs. Does not matter the function is successful or errors out or not. Okay, that's all about differs. It is a very important concept, and we'll use it a lot. Not a lot, but we'll use it quite frequently, and we should remember this pattern. Now we are in the territory of reference types. As I had mentioned earlier, Go has around 5 types of reference types. We have pointers, we have slices, we have functions, and we have channels, we have maps. We have 5 reference types. Reference types basically means they don't have the data themselves. They refer to some other data type. They depend on a different data type that works in the background to have the data. They don't have the data for themselves. Okay. So for now, let's explore pointers. Okay. Now, Go has this concept called pointers. Using using which you can access the address of the variable. And what do we mean by address? Now, throughout the execution of the program, you assign different variables. You create different data types and you assign variables where you store those data types. Now, all those data types, all those variables are stored somewhere in the memory. Let's say this is your memory. There are different slots. You can think of them as those users. They refer to some other data type. They depend on a different data type that works in the background to have the data. They don't have the data for themselves. Okay. So for now, let's explore pointers. Okay. Now, Go has this concept called pointers, using which you can access the address of the variable. And what do we mean by address? Now, throughout the execution of the program, you assign different variables. You create different data types and you assign variables where you store those data types. Now, all those data types, all those variables are stored somewhere in the memory. Let's say this is your memory. There are different slots. You can think of them as slots. So when you create a variable, they are given some slot in your memory, in your random access memory, in your main memory, and they are given some slot. And that slot will have an address. It won't be a physical address because we are abstracted out from the core operating system kernel using the Go runtime. We are executing using the Go runtime. So we are given some address. It's a virtual address. Still, it is some kind of address. We can think of it as a physical address, but it's actually not. So that slot will have some address. And using this address, we use our variables. Our variables are stored in these slots. So what pointers do using this data type called pointer, this data type stores the address of this variable. We use a address of this variable, and we can access the address using this symbol, the AND symbol. And if we have a pointer, we can use the star symbol to find the value of the pointer that this points to. So this is all different terminologies. So let's see an example to understand how it all works. Now here we declare two variables, this I and j. a address of this variable, and we can access the address using this symbol, the and symbol. And if we have a pointer, we can use the star symbol to find the value of the pointer that this points to. So this all different terminologies. So let's see an example to understand. Pointer to an integer. It is not an integer value itself. It is of type pointer, but the pointer points to a value which is of type integer. That's what this means. Okay. And in the next statement, what we do, we print the value of p. A p is a pointer type. P is not a value type. We cannot print the value of p directly. If you do print it, it will print some random garbage value because it is the address. Now we can print the value the pointer points to using this star operator. So the star operator is used to dereference. The terminology here is dereferencing a pointer, and we can do that using this star operator. So we can get the value of p using the star, and we can print it. The next step, what we are doing here is we are taking some value, in this case 21, we are assigning it to this pointer, and we are assigning it to the value of the pointer. And since we have the address, since in this slot, using the pointer, we have the address of the variable, we can change the content of the value, the content of the address using this structure. You can do star p equals 21. Now this address points to a different value. This is 21. And when we print this, print I. Now instead of 42, it will print 21 because using a pointer to I, using a pointer p to I, we change the value of I from 42 to 21 using a pointer. Now, if p was not a pointer, if p was direct assignment, if we did p equals to I, then in that case, if we change the value of p, it would not have shown in the value of I. Since we used then pointer to I, when we modified the value of p, it also modified the value of I, because now both of them point to the same thing. Okay. The next step, we assign the address of j, and we are dividing this value and assigning it to the p, and now the j's value is also changed. And let's run this program and see whether it works expectedly or not. So if we do go and may not go, we get 3 values for 3 print statements. So what happened here? In the first print statement, i's value was 42 because we have not changed it yet. So that's why it printed 42. In the second print statement, we changed the value of I using the pointer p, and we made it 21. That's why we see 21. Same way here, j's initial value was 2701, but after we did this thing, we did some calculation and assigned it to p. And since p was pointing to the address of j using this pointer operator, that's why the value of j is now 73, the result of this calculation. So that's what pointers are. They basically contain a data type which is an address of some variable, and using pointers you can change the content of that variable, whatever it points to. Now there are a lot of concepts in Go related to pointers. We will see it pretty frequently in a lot of different scenarios and a lot of different contexts. So for now, this information, this knowledge is pretty enough, and we'll see what else we can learn about pointers when we add more stuff, more basics to our knowledge of Go. So in the next phase, now let's look at what are structs. So struct is one of the data types of aggregate types. We have 2 types of aggregate types. One is array, and the second one is struct. Array is a collection of similar data types, and a struct is a collection of different data types. So this is how a struct looks like. You say type because struct is a Go's native type. The type, the name of the struct, and you literally write the keyword struct, and then you open the curly braces and you write different data types. You define what are the types of these fields. These are the fields of the structs X and Y, and beside them you write what are the types of those fields. Okay, and how do you use this struct? How do you initialize this struct? Here, if you see, you write the name of the struct, and in the curly braces you provide the values for these fields in that order, in the order that they were defined. Okay. Now we write 1 and 2, and 1 will be assigned to X, 2 will be assigned to Y. And since these are integers, we don't see an error. This satisfies these 2 literals that we are providing. These satisfy the condition. Then that x is an integer, y is an integer, and we are assigning them to a struct which is called vertex. And now we can print this. We print it. 1 minute go, we get this representation, string representation of struct, which is 1 and 2. There are also other the things that we can do with a struct, which is, let's say we initialize a variable and we initialize this struct with x is 1 and y is 2. Now we can access the fields of the struct. The struct has two fields, which is x and y. We can access the fields using this dot operator. We can say whatever the variable is which we initialize the struct with, we can do v dot, and we can use x or y because those are the fields of the struct. And we can also assign some values to the struct. Even though we initialize with value 1 for the field x, we can change the value of x in the next statement, v dot x equals to 4. And now if we print v dot x, it will print 4 instead of 1. Now let's look at how pointers and structs work together, because this is very important. This is something that we'll use a lot when we are building projects. Now what we are doing here is we are initializing a struct with value x as 1 and y as 2, and we are assigning it to v. And in the next statement, we are initializing another variable with name p, and we are assigning the address of v, the address of this initialized struct, and we are assigning to p. Now here what we did is, we using this pointer, we changed the value of x. Instead of 1, we made it this number. Okay. And what happens when we print v here? Let's print it and see what happens. Now we get this number, which is basically 10 to the power 9. We have 9 zeros here. Now that's the point. If we use a pointer and if we have a pointer to a struct, and using that, we can change the values of the fields of the struct using a pointer to a struct. This concept is something that we will use a lot when we're actually building real world stuff. In this example, we're just looking at different variation of defining a struct and different variation of initializing structs. First, run this example, and then we'll see what's happening here. Okay. Now, of this struct. The struct has two fields, which is x and y. We can access the fields using this dot. We made it this number. Okay, integer, and there's one way of initializing struct. The second way is you write the name of the struct and you can provide a key value pairs. You can write the name of the field, in this case x, and you can provide a value. And then with comma, you can provide another value of I, y, and colon 2. You can do it like this. If you don't provide an explicit value for a field, by default, since Go has this concept of zero value initialization, by default, Go will assign the zero value of that data type. In this case, since it is an integer, Go will assign the value 0 to y. Does not matter whether you provided an explicit initialization value for y or not. Go will assign the value 0 to y. That is one way of initializing struct. Another way, what if you don't provide any fields? Just type the name of the struct and you initialize it. In this case, Go will assign the zero value of both the fields to them. In this case, both of these fields are integers, so x will have 0 and y will have 0. Then you can also do this. This is struct little syntax. And what this means is, this is kind of similar to this, but instead of providing the type vertex, p will have the provide pointer to vertex. And if you hover over it, v1 is a type what ampersand, the symbol and stands for. Then for v2 and v3, we have 1, 0, because here we only initialize x with the value 1, and the y was initialized with the 0 value. That's why we have 1, 0. And in this case, we did not initialize any of the fields. That's why x has 0, y has 0. Now, to wrap our heads around where do we actually use structs, we can look at a few examples of our open source repository. Let's search for the keyword struct here. Now, structs are something, if you're a backend engineer or any kind of engineer, and you're using the Go programming language, structs are something you'll use a lot. Your day-to-day life will involve dealing with a lot of structs, because it's a very versatile data structure and very commonly used data structure. If you get some JSON from front end, you have to parse it and store it into a struct before you can use it in your Go program. because unlike JavaScript, you cannot use a JSON directly with your JavaScript object. Okay, you have to pass the JSON into a Go struct, and then you can use the struct. That is one use case of struct. Okay, now let's look at some examples. We'll just skim through them to get a feel of how people are using structs. Okay, so this is one struct which has a field called plan ID and is of type string, and these are called struct tags. And what it says is the key is JSON and the value is plan ID. And it is a bit out of scope for now, but this basically means, let's say from the front end, from the client, we receive a JSON. We receive a JSON with this value. Say plan ID as 3. Okay, this is the JSON we receive from front end. So when we are trying to read it in our handler, okay, first we have to do is you have to take this request body and we have to parse it. We have to unmarshal it into a Go struct before we can use it. We cannot use it directly because it's a JSON type and it is in bytes. When we are parsing it, we can use a struct like this, which has a field, a struct field with Go's own convention. And here we are saying that we are using this struct, and any JSON field with the key plan ID will be passed into this field, this plan ID. So So using these tags, these are called struct tags, and with the key JSON, these tags are one way of mapping JSON fields to our own Go's struct fields, because the naming will be different. In Go, we'll have camel case fields, and the styling of Go is a little different than what we follow in typical JSON-based payloads. That's why we have struct tags, so that we can map the JSON keys into our own struct fields. So that is something a little out of context now, but something useful to remember. This is what a typical struct looks like, and we have more examples of structs. We have this one, invite users. There's a string and there's an array. There's a slice. We have not explored slices yet, and there are a lot of examples of structs in this code base. So you can notice it. First, we have field names, then you have type, and you have tags. Depending on which application, which package is using it, we'll have different tags for a struct, for different parsing mechanisms. Okay, so as you can see, structs are pretty versatile. We can store any type of data inside them. It does not matter what type is. In array, we can only store homogeneous data. In structs, we can store heterogeneous data. It can be an integer, it can be a string, it can be a slice, it can be a map, it can be anything, it can be pointers. Okay, so structs are very useful and something we'll use a lot. And this basics is enough to get us started with structs. Now, another thing about structs that I want to mention here is the capitalizing of the first character of the fields. And as you can see here, all the fields start with capital letters. And this is not a styling thing. This has a use case, as we have seen before. Capitalizing of fields and variables in a package in Go results in that variable or that type being exposed to code outside of that package. So for example, in this, we have this package called CMD, and this is another package called some test package. We see the name here, and the package name is API v1 test. These two are different packages. Now, this package is using code from another package, from the CMD package, and it is using this struct, and it is importing that struct into this package so that it can initialize a new instance of it. What happens if we change this field from a capital R to small r? Let's change it and see what happens. And the moment we made it small case, as you can see, there are errors everywhere in the program, especially in those scenarios where we were accessing the field, this particular field of this struct that we were importing from another package. So that's the use of the capitalizing. If the first letter of that field of a struct is not capitalized, then we cannot access that field outside of that package. That's why we capitalize fields of a struct. And then we have arrays. As I said, arrays are a collection of same type of data types. Okay? That is the one-line explanation of arrays. So what we are doing here, we are declaring an array, same type of data types. Okay? That is the one-line explanation of arrays. So what we are doing here, cannot access that field outside of that package. That's why we capitalize fields of a struct. And then we have arrays. As I said, arrays are a collection of same type of data types. Okay? That is the one-line explanation of arrays. So what we are doing here, we are declaring an array which has this type. It is a string and it can have two items. So this part, this two part, this is basically the size of the array. So when we say two string, we say this, we mean this array is of type two items string. This size is the type of the array also. So this size is part of its type. So this array and this array, three string, these are of not the same types because it is of size 3 and it is of size 2. So that is one thing to remember. The size of the array is part of its type. Okay, next, what we're doing here, we are declaring a variable which is an array of length 2 of strings. And in the first index, we are storing the string hello. In the second index, we are storing the string world. We can access the indexes of the array using this syntax, the square brackets, and inside is the index number. And then we can print it, the index 0, the index 1, we can also print the whole array. The same way, instead of doing it like this, instead of declaring it here and initializing it this way, all the indexes, we can also use this syntax. What this syntax is, we can write the size of the array and we can write the type of the array. In this case, it is an integer of length 6. Then we can provide all the values in this order. 0, the index 0 will have 2, index 1 will have 3, index 2 will have 5, and so on. And we can print this. And let's run this. And as you can see, we have all the expected results. Now, the two major points here are, one, Go is a statically typed language. And second, an array size is part of its type. Now, since we have these two facts, now arrays cannot be resized. Now, because the size of an array is part of its type, you cannot resize an array. You cannot reduce the size of an array. You cannot append to an array. You cannot do any of those things. An array is just a constant that whatever value you initialize it with or whatever value you push to it, and that size will always be the same. You can only push up to whatever value you initialize with. Arrays cannot be resized. And that is the reason you will not see arrays being used as frequently in real world systems. We will still use it when we have a fixed number of elements that we know the value of beforehand. But in most cases, we use another data structure provided by Go, which are called slices. And this is how we can make a slice using an array. And if we try to run this, we get this result of 3, 5, and 7 because this syntax, this indexing syntax that we use to slice. We have arrays. As I said, arrays are a collection of same type of data types. Okay? That is the one-line explanation of arrays. Two types because it's an array using this syntax. So to use this sentence, now the two major points here are, one, Now, since resize an array, whatever this syntax, this indexing syntax that we use to slice, to create a slice out of an array, this is how it works. In the first part, we have a opening square bracket. In the first part, we have this
Okay guys, let's see tomorrow. I think we have completed until functions, variables, loops, conditions, switch case, differ, reference type, structures, structs. Sorry. Tomorrow we need to start slices, map, yeah, slices and maps. Yeah, guys, it was a great session. Yeah. Good night.